So in the next shorter video, we're going to actually look at the pericyclic reaction that's happening here, right? This kind of on-screen electrocyclic reaction of butadiene, okay? To actually make those four-membered rings we saw at the beginning of the first video, right? So we have to think about here, right? I kind of drew it a little bit differently, but we need to remember, or what we want to do, sorry, is that we want to kind of line up the alkenes here to make it a little bit easier to view. Right, so we kind of want to have it like this, where we have our alkenes here, where we have our 4 electrons, or 4 carbons, we kind of just drawn it a little bit differently, and we want to kind of draw our CH3s like this, right, which looks now similar to what we had in the beginning of that first video, remember? And of course making sure, right, our alkenes are still making sense, right, we still have things E-oriented, right, the methyl group, and the rest of the chain here across each alkene is on opposite sides, right, E, so we're all set here, right? We just rotated this middle carbon-carbon bond. And so what happens over the course of this reaction, right, the mechanism that actually takes place, as long as we're using heat or light, is that we have the alkenes actually reacting with each other. So this alkene will actually come out and attack this carbon, and the other alkene will come in the middle here. So this is the actual reaction taking place, and the product we get, again, depending on whether we use heat or light, we end up with this alkene here. And whether we have the methyl groups on the same side or opposite, right, cis or trans, depends on the heat or light we're using. And it's not as simple, and we're using squiggly bonds here to denote that we have, right, could have a mixture of chirality. What we actually get, right, either cis or trans alkene depends on the molecular orbitals, right? Heat won't always give us cis, and light won't always give us trans, or vice versa. It depends on the molecular orbitals. Because they're kind of like mechanisms, we need to know what we're considering. So I've drawn out the molecular orbitals already here, right? We have our 0 energy in the middle, and right, we have 4 electrons. So we know we're filling it up like this. And we have our 0 node, 1 node, 2 node, and 3 node situation happening, okay? And so if we're thinking about heat versus light, let's think about heat first, okay? This is the situation. Light's going to react with it differently, but heat, everything reacts as is. And to get this reaction to take place, right, what's actually happening is, right, to make a new bond, right, for this reaction to occur, right, these pericyclic reactions, we need direct overlap of the p orbital. Okay, and so what do we mean by that? So let's take this, right, this hexadiene here, and let's go ahead and draw out the orbitals on the actual reaction, or on the actual molecule. Okay, so we're just thinking about, again, these pi orbitals. And so we want to draw the highest unoccupied molecular orbital, right, which is here. And so, right, we're kind of drawing these molecular orbitals on the actual molecule. Right, we have our 1 node there in the middle. And so what's happening is, right, we need these orbitals here, right, to overlap. These are one of the ends here, right, because this is what's closing, or we're getting this hexadiene here to close up. So we want to get these orbitals to overlap. And so what's happening here is that these groups are swinging around, and I'm showing this as an arrow, but this isn't a mechanistic thing, right? We want to have our we want these orbitals to overlap, so we're going to swing around these orbitals to get it to look like this. And so we have, right, this left orbital where we have that sort of the white lobe pointing towards the right. Our methyl group is now pointing down, and then on the right side we want the white orbital pointing to the left and our other orbital pointing to the right. Right, so see that we kind of swung the orbitals around, and we can kind of visualize this with our thumbs, which I'll demonstrate more in class. But this sort of system that's happening here is something called conrotatory. Sorry about that. Right, we have so this is something called conrotatory. And so what's happening here is we have, right, as the name implies, right, things are moving in kind of the same direction, right, conrotatory. And so the orbital on the left here, right, that orbital is, right, we're swinging this counterclockwise, and we're also swinging this right orbital here counterclockwise as well to get them to line up. And so the methyl groups are going to follow that same swinging, right, the methyl group's pointing down, this white orbital, to get it pointing in phase with the other, goes up. Right, and so this transformation that takes place, right, the final alkene we get at the end is going to look like this, where we have the groups pointing in different directions. Okay, so this is what happens with heat. So with light, we get sort of the opposite situation, right, like we showed at the beginning of the chapter. So let's go ahead and take a look at that. And I'm going to erase some of what's on the screen now to give ourselves some more room. Okay, so take a minute, pause the video if you need to make sure you have this jotted down. And I'm going to start this on a separate page, or on the same page, but for you might need a separate page. So we have conrotatory. So for disrotatory, we're going to see something different. Okay, so if we use light, what's happening now is the electrons are going to be moving. So light, right, we're giving more energy to the system, right? Light is implying that we're adding, right, we're adding these electrons, we're adding this energy to make the electrons jump up in energy. So now our HOMO is here, right, for light only. Because light, right, we're adding these photons, the electrons are going to jump up. And so we're going to get this situation where now, right, if we're going to redraw in our system here, right, putting in our orbitals, we see the overlap is going to be different now. Right, again, mimicking what the HOMO looks like. Right, see, to get these orbitals to overlap now, they're going to have to swing around differently, okay? So to get the, again, sort of the white phase here to line up, we're going to have, like I just mentioned, disrotatory. So they're going to be swinging in the in the opposite directions. So one's going to be swinging counterclockwise, again, to get that white orbital over to the right, and the right side is going to be swinging clockwise, which we can show with our thumbs, but it'll be easier for me to show you that in class. Okay? So now they're both pointing down, and so our alkene here is going to look like this. Right, so again, I know this is a lot of new information to take in, right? We're looking at reactions in a different way now, right, rather than just a straight-up mechanism. Right, the mechanism still matters, but we don't get any of this dis versus conrotatory information without right, understanding the molecular orbitals. Okay, so we're going to get a lot of practice with this in class.